Okay, so the effective interest rate. The effective rate, also known as the annual yield or the normal rate, is the simple interest rate which would yield the same future value over 1 year as the compound interest. So here below we have an equation for effective interest rate where we have 1, open parentheses, 1 plus r over n raised to the n power minus 1. So here we only still need to be able to identify for E, which is the effective interest rate, N, which is the number of periods of year that it's calculated or compounded, and R is still going to be our rate. All right, so make sure, I've had some students to do this before in the past, but make sure that you don't do this. Because we have a -1 on the outside and a positive on the inside, they don't eliminate each other. They have nothing to do with each other. Because remember, with the order of operations, we have to do everything that's inside the parentheses first, which still means executing and adding that 1 to whatever number you have, and then raise it to a power before we even subtract. So I just want to make sure if you were confused on that, please do not be. So we have our first example. It says find the effective interest rate when the stated rate is 4% and the interest is compounded semi-annually. So here we can still do like we've been doing from before, and because we're using E, we're looking for the effective interest rate. We have an N and we have an R. Since it's compounded semi-annually, what would N be? Semi-annually. How many is that? Semi-annual. 2. What's going to be our R? 0.04 for 4%. So now we take our effective interest rate equation. I left my calculator upstairs. Or in the car somewhere. The first thing we can do is plug in the numbers that we have. 1 plus R, which is 0.04, over N, which is 2, raised to the second power, minus 1. Everybody at least with me to this point? Special? Just making sure that's on the road. All right, so somebody give me 0.04 divided by 2. 0.02. Thank you. So now our 0.04 change to 0.02. Now we just add inside, which is 1.02, and we can raise it to the second power. Can you give me that as well? 1.02 squared. 1.0404. So that's what we got from 1.02 squared, or to the second power. Now we just subtract 1 to get our answer. Our answer is 0.0404. But remember, we're looking for an effective interest rate. So how is rate found? So in that problem, how is our rate given to us? A percentage. So we have to change this to a percentage, which we do what? 2 places to the right. So our answer is 4.04%. Like I said, you don't have to use that many steps, but I'm just showing you step by step how to do the process. Any questions? Okay. All right, so I'm gonna let you try this one, and it's kind of 2 in 1, but it's the same thing, and I'm gonna leave this here so you can work it on your paper. It says, which savings account is a better investment? We have 6% compounded quarterly, and we have 6.2% compounded semi-annually. So that means we're going to take our same equation, identify what we have for both of those, and then solve. I'll give you about 2 or 3 minutes to do so, and then we'll work it together. Can I erase this? Yes, okay. So the first thing that we're gonna do for both is identify what we have. So we have 6%, which is 0.06, and it is compounded quarterly, which is 4. The second one, we have 6.2%, excuse me, which is 0.062, and it's compounded semi-annually, which is 2. Did everybody get there with identifying what they had in the problem? Semi-annually 2?
Wait, so we do two different,
Mhm.
ones or? Oh, well.
Because it's asking you to compare 6% quarterly or 6.2% semi-annually. So that means if we come over here and we have E is equal to 1 plus R over N, raised to the N plus 1, minus 1. Plug in 1 plus 0.06 over 4, raised to the 4th power minus 1. Can I get 0.06 divided by 4? 0.015 minus 1. So this is just us actually executing 0.06 divided by 4. Next step, just add what's inside, 1.015 raised to the 4th power. Can I get that math, please?
1.0613635551.
Minus 1. So we get 0.063, 1363551, which we can round it up. So let's go ahead and make it into a percentage. Then we get 6 point, I'm going to say
Well, you get put.
14. So the 0, okay. 14, okay, sorry. So what I did was mixed up some stuff here, because I wrote it like 3 times. Well, I don't know what that was. So for our first problem, we get 6.14%. Second problem, plug in 1 plus 0.062 divided by 2, raised to the 2, minus 1. Can I get 0.062 divided by 2?
0.031.
So all we did is 0.062 divided by 2 is 0.031. We're going to add that together inside the parentheses. Can I get that squared, please?
1.062961.
Minus 1. And we get 0.062961 because it has to be a percent. 2 places to the right. 6 point. Since we have to raise this to make that go over, we're going to get 6.3%. Well, we had to round up. So which savings account is actually better? 6.14% or 6.3%? Savings account?
Just 1.
The only reason why 6.3 is better is because you're getting a couple pennies more, basically. Just higher. Because technically, we can say that that's 6 cents, but that 0.2 gives us a little higher amenity when we're saving money. Now, we had to pay out, like a loan percentage, the 6.14 would have been better. Any questions? Got it? Kind of? Okay. All right, so now we're going to talk about annuities, and you may have heard plenty of commercials that talk about annuities, but an annuity is a savings investment for which an individual or business makes the same payment each period. So that can be annually, semi-annually, quarterly, weekly, etc. into a compound interest account where the interest does not change during the term of the investment. So with compound interest, what that means to us is, as it's compounded each of those times, the only thing that doesn't change is the actual rate itself. The total amount accumulated is called the future value. You remember when we talked about A in those last couple of problems, the A equals P plus I? The future value is the total amount you will pay over a period of time. Annuities are typically set up by individuals to pay for college expenses, vacations, retirement, or whatever you want to do, but you can start saving now for something later. Okay, so you remember with compound interest how we actually did it by hand before we got the equation? That's what we're about to do now. It says find the future value of an annuity where a $500 payment is made annually for 3 years at 6%. So well, actually, we can do it this way. So every year we know we're paying how much for sure to save. 500, right? So that means at the end of the first year, the interest rate is still going to be 6% and the payment is still 500. So at the end of that year itself, that payment is only 500 because you're putting in to save. Year 2, we're going to take the 500 that was already collected and we're going to gain 6% interest. Then, because it's at basically the end of the year and you have to make another payment, we make our payment of 500, excuse me, and the value of the annuity is going to be pretty much, I have like 500 from year 1. At the end of year 2, we're going to do 500 times 0.06. Can I get that in calculator? 30. So we got 30. So that's a total of 530 plus a $500 payment. So this is pretty much year 1 plus the interest, which is 530, plus the 500 from the end of year 2, which is 1,030. So now at the end of year 3, same situation. We're going to take what we already have in for year 1 and year 2 plus the interest, which is the 1,030. Multiply it by 0.06. May I get that, please?
61.8.
Thank you. And now we still have to add, hold on, let's add that to the 1,030. $1,091.80. And we still have to pay that last year's annuity price, which is 500. So at the end of 3 years, you should have $1,591.80. Where 500 is what you saved, and the $91.80 is interest that you accrued over the time. Now by hand, this thing's kind of, if it's like 25 years, this will be long and complicated, correct? So we're going to shorten that up. And we're going to get an equation for our future value of an annuity. Now it may look long, but it'll probably be longer than you writing this out for years and years, right? It's just substitution. You got it. You got it. Y'all got it. All right, so we have A is equal to R, 1 plus R over N, raised to the NT minus 1, over R over N. All right, so the big R is going to be the actual payment. Like we had 500 in the last problem. R is going to be the payment for the annuity, the regular payment. R is still the interest rate. N is the amount of months per year, or the amount of time the payments is made per year or compounded. And T is still the amount of time. So now one thing I still want you to understand, A is the future value. That means every cent you will pay for the item. Every cent you will pay, or every cent you will gain, is still the future value. Okay. So here, they give us a problem. We're going to find the future value of an annuity when the payment is $800 semi-annually and the interest rate is 5% compounded semi-annually and the term is 4 years. So let's write what components we have. A, have big R, little r, N, and T. We know we're looking for the future value. They told us we pay $800, which is the payment, which is R. The rate is 5%, which is 0.05. N is going to be semi-annually, 1. And the time is going to be 4. Oh, 2, sorry. You're correct. I'm sorry. And I said it and said it and still put it up there. I apologize. But does everybody understand where we got the components from? How we got them out the problem? Okay, so now we just take our equation and we sub in. And just like the other problem, like I told you before, where you can't exclude the ones and ones, you can't do the same here. You can't exclude R over N and R over N because this R over N is within our term of the numerator. Next thing, let's plug in our numbers. Alright, so simplifying this is a little bit simpler than the actual compound interest equation. The reason why, we have the same numbers right here, don't we? So that means we don't have to find this one once and execute our exponential function once as well. So can I get the 0.05 divided by 2? 0.025. 0.025, thank you. This, I forgot that fast. 0.025?
Yeah.
Okay, sorry. Then we have 2 times 4 is 8, minus 1, over 0.025. So you see how the problem starts to begin to look more simple at this step, sorry. So now we add what's within our parentheses. 1.025 raised to the 8th power. Can I get that number, please? Can you start over?
Sorry.
No, it's me. Can you start over?
1.218402898.
858.
898.
Okay, thank you. And we subtract 1 over 0.025. Next thing, just subtract here. So we have 800 multiplying it by 0.2198402,898. And then we divide it by 0.025. Can you give me the 0.219 times 800? I'm just doing it step by step right now.
974.5.
And then now we just divide it by 0.025. What do we get?
38988.
38. Like 38?
Yeah.
Or 398. I mean, or 389.
38988.
Everybody get the same thing? We all somewhere. Can we do this again? 800 times the 2.19. I left my calculator in the car. I'm sorry. Anybody? Somebody? I'm just looking for this multiplier together. 800 times 0.29, 2198402,898.
174.722318.
77.
722318.
Okay.
18.
It's me in numbers. I apologize. Okay, so thank you. You did well. So the point of us doing what we're doing step by step like this is to see where we messed up. But the whole point was if it was just a simple, multiplication problem, that's something to go back on that's easier. But you don't have to do all these steps, but you see that it kind of takes all these steps to really actually get your answer. Connect Math is very sensitive. If you put it in there, if you round too early, it will give you the wrong answer in your calculator and it will be wrong on Connect Math. So if you went in here to this number to 1.218402, etc., and actually rounded here, your answer would not be the same answer and it would be incorrect on Connect Math. So make sure if you can, you write your full numbers or document your full totals until you get to your last answer and then round. But if you notice, all we did was what? Substitute and order of operation. Anybody have any questions about any of these steps within here? Did somebody get confused somewhere in here? Who just think it's wrong? I'm being honest. I need to know where we at here. Who think it's hard? Who think it's long? Who just don't want to do it? You honest? But can you do it? That's really the question I'm asking. Where did you get stuck at? Were you here with us? Were you here when we subbed in? All we did was plug these numbers into that equation here. I'm confused.
It's like this steps was going back and forth, so I was like, I'm thinking which.
And it is, but okay, so I'm gonna try to explain it so you can get what I'm saying. You knew how to find the numbers, right? All I did was plug in big R, 800. Brought down the 1 because it's a constant, 0.05 over 2 because it's R over N. 2 times 4 because it's N times T. Minus 1 and still our R over N, which is 0.05 over 2. You get where we are now? Okay. This step, all I did was work my parentheses first and did my division. So that's where we got the 2.025 in both spots because they're the same thing. Multiply 2 times 4, which is 8. That's all we did. This step, all we did was added 1 plus 0.0, order of operations, still working on the inside of those parentheses. And we got 1.025. Now, we took that because it's still within inside a bracket, which is like the parentheses. That's why I stayed here so long. Because we did 1.025 raised to the 8th, which is the 1.218402898 minus 1 still, because our constant still comes down. At this step, we subtracted the 1. That was it.
I messed up. I forgot to subtract the 1.
Okay, so once we got to this step, all we did was subtract the 1. So now, all we did was multiply the numerator. Got the 1.747222318 divided by 0.025, and we got our answer. So it's really order of operation every step. I just do one step at a time, other than right here where we transpose those at the same time. Well, at least you saw where you messed up. That's the whole point. All right, so here, what time is it before we get here?
2:36.
Oh, okay. I got time. So now, what do we notice that's the difference here? We got R in front, right? We're looking for the payment. So we know how much it costs at the end, which is the future rate. Now we're solving for R. So we still have the same components. Big R is the payment, that's what we're looking for. And everything in the equation really transposed. Now we have A times R over N. And then we have in the bottom, 1 plus R over N times NT minus 1. Did you point at the camera? Okay.
This is gonna be, when you
That-
post the
mhm.
video, so go back.
Yes, ma'am. So this is our new equation. We use this one when we're looking for how much we're gonna end up paying by